So in this part of the screencast, we're going to talk about how do we do the derivatives of exponentials and logs if they have a base other than e. So we know how to do the derivative e to the x, and we know how to do the derivative of ln x, both with base of e. How do we change that? So we're going to basically use change of base and change them into e's so that we can take the derivative. So this first one, we're going to deal with the exponential first. If I have a to the x, we're going to write it so that it is a base of e. E, and then we're going to do this little math trick, ln a times x. Now, this part kind of cancels. This ln a and the e, they're inverses, so that ln and the e cancel, so it'd go back to a to the x. So really, that is a to the x power. I have not changed it. I've just rewritten it really weirdly so that I could have it be in a base of e. All right, so now if I take the derivative, it's taking derivative of an e. Well, you know how to take the derivative of e. Its derivative is itself. Now those parentheses I keep putting there because ln of a is just a number. A is the base, 2, 5, 10, whatever your base happens to be, but it's a number. It's not a variable. So that's a coefficient in front of x. So when I go inside of my e to the x to take this derivative, the derivative of some number times x is just that number. Like if this were 3x, you'd say, well, the derivative is just 3. Well, it's ln a times x, and that ln a is just a number, so it's just times ln a. Now, as we kind of started out saying, this e and the ln cancel, so I'm back to having a to the x power, because that brings the a down as our power, but I have to multiply by ln a. So the derivative of a to the x is a to the x times ln a. Because we can rewrite anything with any base, it just changes the power. It still has, it's like e to the x, it has its own derivative, but because it's not exactly e to the x, that is the correction factor for it not being e to the x. So derivative of any exponential is itself times the correction factor of natural log of the base. Now, how about derivative of logs base a? Well, first we're going to rewrite again. So we have to use change of base formula. If you don't remember change of base formula, it's log x over log a, but we're going to use natural log because we know how to take the derivative of natural log. So we're going to have natural log x over natural log a. All right, so if we're going ahead and going to do that, remember that just like over in the previous derivation, ln a, is just a number because a is just a number. So really this is 1 over ln a, which is just a number, a coefficient, times ln x. All right, so I'm really taking, oopsie, I need my derivative out there. I need to take the derivative of this crazy looking thing. All right, 1 over ln a times ln x. And this 1 over ln a right here, that, my friends, is just a number because a is just a number. So my derivative is going to have that coefficient of that crazy number. It looks like a crazy number times the derivative of ln x. Well, the derivative is just 1 over x. So my derivative looks like 1 over x ln a. So again, it's almost exactly the same because logs can be written in any base. Its derivative is just like natural log with the correction factor for the fact that it's not in the base of e. It corrects for that by multiplying by the natural log of a. All right. So now if we're going to actually use that to take derivatives, if I'm going to take the derivative of this exponential y prime, it's just the same as if it's e to the x. It's derivative itself, but because it's not e to the x, you have a multiplying by natural log of 2. Done. Okay, and how about this? If I take the derivative of 4 to the 3x, the derivative is 4 to the 3x don't forget you have to go do chain rules, so times 3, times, don't forget, it's not e, so you have to do multiply by ln 4. Okay. I don't care which way you do it. A lot of people do 4 to the 3x times natural log 4 right away, then times 3 inside. Up to you. I kind of like doing it the second way myself so that I don't forget. Now, most people say you should put that ln and that 3 and this ln2 out in front because they're coefficients. So if we're being really particular, you should put 3 ln 4 times 4 to the 3x. I always put that in there because it makes it really clear that that is not part of the 4 to the 3x and that this is not part of the ln. That is just my particular thing that I do. All right, so now, what if I'm taking this derivative down here? So again, derivative of an exponential is just itself, but since it doesn't have the base of e, we have to correct for that base of e, so ln 5. Don't forget to go inside and take the derivative inside, so 4x. Done. We just should probably rearrange it a little bit so it's more conventional. 4x in front, natural log of 5, 5 to the 2x squared minus 1. I always put my ln's in parentheses just because it looks a little crazy if you don't, in my opinion. All right, so let's do this last one. Now, if I want to take the derivative here, again, the derivative of an exponential is simply itself, so there you go. Copy the whole thing down. But since it's not an e to the x, you have to correct that by multiplying by the natural log of the base. Now, you still have to go inside and take this derivative, which is a chain rule, so 5 times 3x minus 1 to the 4th, because we brought the 5 down and changed it to a 4. But now we go inside of that and take the derivative, so multiply by 3. So that is a little nutty looking here. So I have my coefficient of 5 and 3 here that I'm going to multiply together. That's 15. I have another coefficient of ln 10, which I can't combine with anything, so I'm going to multiply it there. I have this crazy polynomial to the 4th power. Let me make that look like an actual 4. And then I also still, I don't know if that's any better, I also still have this exponential attached to the 5th power. So 15 ln 10, 3x minus 1 to the 4th power, and 10 to the 3x minus 1 to the 5th power. And that's your derivative. I don't know that I would do anything more to simplify because, again, this factored form is actually a really nice form for using to solve problems. So what about if we have to take logs and do derivatives of logs? Let's just do a couple examples. So this one is a log. It's just like ln. So 1 over 5x plus 1. That 5 doesn't even look like a 5. Let's try again. And since it's not an ln, you just have to remember you have to make a correction factor for that by doing ln 4 on the bottom times, now we have to do the derivative inside of here because we just did the log part. Okay, so times 5. I often cheat and just go boop, ba-doop, 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 and put the 5 right up on top to begin with to save myself some time and energy. All right, if you really want to multiply the ln 4 through, go for it, but it's not necessary. Now, how about this one? If I take the derivative, don't forget that there is a base right there of 10 without them saying it. Log without a base on it means base 10. So we have 1 over, it's a log, so just like natural log, it's 1 over whatever's inside. But since it isn't a natural log, you have to do a correction factor, so you have to have natural log of the base 10. Now you have to go inside and take the derivative inside, so I just cheat and write it right up on top. The derivative of cosine is negative sine, and you're done. But there is one thing. This right here, sine over cosine, as soon as you see that, I hope you're going, ooh, warning, 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 that is tangent. So you're going negative tangent of x, and you divide that by ln 10, okay? Because the ln is still on the bottom. Sine over cosine is tangent. There's a negative involved, that's why it's still negative. But the ln 10 is on the bottom. All right, so you can go ahead and do the chain rule on this one, but I'll be honest with you, I used my log rules right away and said, oh, that 4 right there, I'm moving it to the front. So I changed it to y equals 4 log 17 of x squared plus 3. So I didn't have to do the chain rule inside the log. All right, so now I'm going to go ahead and take the derivative, y prime equals, and then I have 4, because it's a coefficient, I can just leave it at 4. And then the derivative of the log. Well, the derivative of the log is 1 over everything inside the log, x squared plus 3. And then I have a log that's not an ln, so I need to have the correction factor of ln 17. And then I have to go inside of here and take the inside derivative, so 2x. Now, y prime equals 8x over ln 17 x squared plus 3. And you're done. You can go ahead and do it by chain rule, which I actually tried first, and it takes quite a few more steps, but I didn't see that at first, so you might not. It works. You could do it. There's lots of extra canceling that you have to do, but if you do it this way, then you save yourself some steps. Same deal in this next one. If I see right away that I can use my log rules to split this up into lots of logs. So this is log 6, and remember this is a half power when it's a square root. I am going to say it's log 6 of x plus 3, but that 1/2 power, that's there, I'm going to move down in front because that's a rule, and it makes my life easier if I don't have a power because I don't have to do chain rule. And then because it's division, I'm going to subtract log base 6 of 2x minus 1. And that guy didn't have an exponent, so I don't need to bring anything in front. So there's no exponent there to bring down in front right there, so I don't have to. All right, so now I can take the derivative, and it will be a lot easier. I won't have to do any quotient rule because I got rid of the quotient, and I won't have to do any chain rule. Well, I won't have to do extra chain rules because I put that exponent down in front of the log. All right, so now I'm going to take the derivative. I'm leaving the coefficient because it's just a coefficient. Derivative of any log is just 1 over. All right, I'm going to put that in parentheses because I feel more comfortable that way. But since it isn't a natural log, I have to take that into account. So I need ln 6 to make it, to correct it for that it's not an ln. All right, so that's that derivative. Now, I guess I should say go inside of here and take the derivative. It's 1, but it doesn't change it. So the derivative inside of there is 1. All right, now this one doesn't have a coefficient, so I'm going to do 1 over 2x minus 1, but again, it's not an ln, so I need the ln 6. Now go inside of here and take the inside derivative. So that's 2, just 2. Got a little excited about writing my x, and I'm going to kind of erase this one here because I don't need it. So there's my derivative right there. I'm going to simplify it just a little bit, and I think that if you were looking in the back of your book or something, they might be real excited about changing this to one fraction. I don't think I'm going to bother. Although it's not awful to do, it's not fun either. Now, the 2's cannot cancel because the 2 is not a factor down here. It's a term. It's part of this term. It's part of that factor, but not the whole factor. All right, so I'm going to leave the ln 6 there and the 2x minus 1 there. I'm not so sure it's worth your time and effort to go ahead and do anything more to that. If you have to solve for 0, we'll deal with how to do that later. All right, so we're going to sum this all up. What if I have to take derivatives of several weird-looking things? Well, what about e to the e? If I take the derivative of e to the e, remember e is a number raised to a power. So that's like saying the derivative of 2 to the 3rd power. Well, that's just a number. So the derivative, 0. All right, because that is just a constant in here. That's just a number, no variables. Now, derivative of e to the x, that is one that we learned. Derivative of the e to the x is my favorite derivative. It is its own derivative. The derivative of e to the x, just e to the x. Let me get rid of this stray mark there. All right, now, if I do the derivative of e to the 2x minus 4, again, e is its own derivative. It's the best thing ever, e to the 2x minus 4, but you do have to do chain rule, so you have to take the derivative inside, so there's a 2 in front of there. Now, what about if I go up here and do the derivative of x squared? Don't forget that the x is not in the exponent now. It is the base, so you have to treat it like a polynomial and do the power rule. Lots of people like to try to treat it like a to the x, and that's not true. When it's a to the x, that is when the base is a number, not a variable. The variable is in the exponent. Now this guy right here, x to the e, we're going to go ahead and do, well, that is exactly the same idea as this guy up here. So you bring the power down and you subtract 1 off. All right, it's a decimal. I'm going to leave it as e minus 1 so that I don't have to write a crazy decimal because it's more exact the way I wrote it. Now this last one is tricky. All right, so that one you can't do by using either the power rule that we were just talking about on the last two or the base rule because the base is an exponent. So neither one really works. We're actually going to have to use a trick to take the natural log of both sides. So we're going to do that. Okay, we're going to take the natural log of both sides. I'm going to move this whole thing up if it'll let me. I'm going to have to move it piecewise. Ooh, that's fun. All right, so we're going to take the natural log of both sides. And then this side right here is really going to look like x ln x equals ln y, natural log y. And you can bring that x down in front is what I did over here. So now if I take the derivative, because now I can, I get 1 times ln x, because I got to use the power rule, product rule, excuse me, plus x times 1 over x. So those are going to cancel to be 1, by the way. And then we have 1 over y, dy dx, because you have to go inside and take the derivative inside, which is dy dx. Now, to find the derivative, dy dx, we have to multiply both sides by y. We're going to do that in a second. First, I'm going to simplify over here. We get ln x plus 1. And then I'm going to multiply both sides by y so that on this side it's y and on this side it's dy dx. All right. Now we know y equals x to the x power. So we have ln x plus 1 times x to the x power is my y prime or my dy dx. So there you have it.